Hi, welcome to Coursera's Instrumental Analysis class. I'm Vicki Colvin. This is Lecture 5 in Week 2, and we're talking about atomic emission spectroscopy. There's a companion demo, so this is going to be a pretty brief lecture, just saying some of the highlights, and definitely do the reading, because I'm really counting on you going through that to learn a lot of the facts. So I love this picture because I think it really captures in a very graphical way what goes on inside of an atomic emission spectrometer. So in atomic emission, you're taking a sample and it's a liquid form and you're vaporizing it, you're turning it into droplets, and then you're putting it in a torch and you're just heating it up. And in the process of doing that, you're actually causing atomic emission, which is what's visualized here as that orange color. And in this case, you're measuring calcium. And because the concentration of the calcium scales linearly with the amount of light that comes out of the system, if you measure the amount of light that's present, you can actually quantitatively determine how much calcium's there. If you also remember from my earlier lectures, if you can measure the wavelength of the light, you can also figure out what elements might be present. So atomic emission spectroscopy, like most of the atomic spectroscopies, doesn't just tell you how much of something you have, but it tells you what you have. It does both qualitative and quantitative analysis. So a little bit about acronyms. So you're going to hear, this method is going to be called ICP, just ICP alone, which is a poor nomenclature because that stands for inductively coupled plasma, which we're going to talk about in a second. The real guts of the spectroscopy is held in the OES, optical emission spectroscopy. You'll also hear it called atomic emission spectroscopy. So you're going to see ICP OES and ICP AES, and they're going to be used interchangeably. I'll usually call it OES myself, but sometimes I'll slip and call it AES. So just a forewarning there. Here's some of the most important facts to know about ICP AES. Now, if I could only choose 3 that I would really want you to know, I think the 3 things I'd want you to know are, first off, atomic emission spectroscopy's big claim to fame is that it can simultaneously measure multiple elements. And that can be really important if you have a problem where you're after, let's not just say lead, but maybe 5 or 6 or 7 other elements, and you want to measure them all simultaneously. That's really hard to do in atomic spectroscopy. That's absorption-based because you need different types of lamps. But it's really easy to do here because you're just collecting the light that's coming off of the sample. The other thing I'd want you to know about it is that it's got a pretty good detection limit. We're going to talk more about detection limits in the next few lectures, but it's a good, solid spectroscopy, except you need a pretty clean sample to work with. It will be more expensive than AAS, as you'll see. So what does a spectrometer look like? Let's go inside the black box. You first have to figure out what the black box has to do. Well, you got to atomize your liquid sample to create a dense gaseous sample. The more density you have in the gas form, the better your signal, because you want as many atoms emitting that light so you can collect a lot of that radiation. You're going to have to excite your sample. This is a really important part of AES, and in fact the term inductively coupled plasma is exactly this piece. In AES, you're really watching the excited states of atoms go back to the ground state. In absorption, what we just talked about, you're watching the ground state go up to the excited state. So that's a really big difference. So you have to collect emitted light. Finally, you have to detect the light and discriminate the wavelengths if you want to fingerprint what atoms might be present in your sample. So here's a diagram. This is a simple block diagram of the system. Go ahead and take a look at it. And I'll tell you about the most important components. So one of the most important features of the system, I think, is the inductively coupled plasma part. You're going to see this a lot, and it's a really cool thing because it's actually the same temperature as the temperature of the sun inside of one of these plasma torches. So a little bit about what a plasma is. A plasma is a dense gas of ions. And in this case, what's happening is argon gas is flowing in to this sort of torch. And also, you can have a buffer gas behind it, and you're also dealing with your sample itself spraying in. So it's a pretty complicated flow control problem. But nevertheless, the atoms from the argon are being formed, and they end up going into what's called an RF coil, where there's an oscillating electromagnetic field there. Now, if they're just neutral atoms, they're just going to sit there. But there will be a spark that has to happen. And when the system sparks, it just happens once, or you sometimes do it a lot of times. It's kind of like starting a lawnmower. But once you spark it, you get some ions forming. And in an electromagnetic field, ions do something totally different. They start moving around. So this RF frequency, radio frequency field, is sloshing back and forth, and neutral argon doesn't do a thing. Charged argon starts to slosh around too, as it moves with the field, and it slams into other argon atoms over and over, and those lose electrons and then they come back down. To make a long story short, the sloshing back and forth of the ions causes other ions to basically ionize, so they lose their electrons, and you have a soup of electrons, cations of argon, and neutral argon all sitting there. But you have a lot of flow of ions back and forth. It basically keeps the whole thing kind of really, really hot. And you create a plasma that way. And so the RF coil is basically inductively coupling to this plasma. And that's the color you see here. It's very, very hot, about 10,000 Kelvin, equivalent to the surface of the sun. And that's actually what's going to be making the emission that you see. Now, you don't really want to ionize the atoms that are present in your sample. You just want to get them up to those really, really excited states so they fall back down. And I really would encourage you, if you want to know more, I found some really good reading material I can share with you that talks all about these ICP torches, how they work, and a little bit about the history of how they were designed. But they're one of the most important and finicky parts of this instrument. The other thing I just want to point out, and it's in your reading material, is that often when you buy an ICP OES system, you have to make a choice between radial and axial detection. And shown here and is kind of the examples you'll be reading about. But the bottom line is that when you have this torch, you can collect light from the sides. So it's like looking at the side of a candle, or you can look straight down on top of it. And by looking straight down on top of it, you have a larger path length of interaction, and you get many more photons to count. So your detection limits are going to be better. So the radial versus axial detection is going to control how low you can go in the detection of elements. And so that becomes one of the instrument choices that you have to make. It's also more expensive, but of course it comes with this capability of measuring to lower detection limits. So I encourage you to watch my demo lecture where I show you an ICP AES that my own lab group uses quite a bit in its research, and hopefully it'll be fun to see what the instruments look like. And as you'll see, we're measuring chromium in that case, and rather than just looking at one wavelength of emission, we actually have it tuned to several. And that's actually one of the ways in which AES can be a better quantitative instrument than absorption spectroscopies, because you can actually get a lot of different wavelengths, and by collecting all that data simultaneously, you can get much lower random error. So that's another advantage that you'll see with atomic emission. So thanks so much for joining me, and I'll see you next time.